So before we move into the discussion on Banach fixed point theorem, we'll see some preliminaries that are required to understand the theorem, and possibly you might have already seen those preliminaries. So in such a case, you may skip this lecture and directly move on to the lecture on Banach fixed point theorem. But if you have not seen these, then we can you can stick on to this lecture till the end. So the first notion that we'll discuss is that of normed vector space. Okay, so this lecture is on the assumption that you already have an idea of what vector spaces are, what properties do they possess, and you have some idea about norms and inner products defined on a vector space. Okay, so basically you have a clear idea of what vector spaces are. Okay, now a non-vector space is basically of this. So vector space V is called a normed vector space if to each vector V in this set there is a real valued function, which means the function takes in the vector as an argument and gives a real number. Okay, there is a real valued function which is defined as this. Okay, this is the norm, what we call as the norm. So this real valued function satisfies three properties. Okay, one, we'll call this function as a norm. Okay, so the norm of V is greater than equal to 0. This is true for all. So whatever vector you take from the set capital V, the norm of this you will always be greater than equal to 0. Okay, and in addition to this, the norm of V will be 0 if and only if the vector V is 0 itself. So other than the 0 vector, the norm of V will never be 0. It will always be a positive quantity. Okay, if the norm of V is 0, then the vector itself is 0, and the norm of a 0 vector is always going to be 0. Next, in this part, what will be interested in is discussing about real vector spaces. So vector space are associated with field. So when we say real vector space, that means the field under consideration is real. Okay, so the norm of a scaled vector, okay, where alpha is the scaling factor, is same as scaling the norm of the vector V by the magnitude of alpha. Okay, this is again true for all vectors in the vector space and for any scaling factor that you, any real number that you take. Okay, the third is if you take the sum of two vectors and take the norm of it, then this norm will always be less than equal to the sum of the individual norm of the vectors. Okay, this again holds for all vectors on V, and this is sometimes known as the triangle inequality. Okay, so a vector space V is said to be a non-vector space if you are able to define, if you are able to have a valid definition of norm associated with the vector space. Now, a norm is basically a real valued function which satisfies all these three properties. The norm of a vector is going to be greater than equal to 0, and if it is 0, it is only 0 when the vector itself is 0. Then if you use a real number to scale a vector and take the norm of the scale vector, then this is nothing but equal to the scaling of the norm of the vector v by a factor of magnitude of the scaling factor alpha, and then the norm of the addition of two vectors is always less than equal to the individual norms of the vectors being added together. Okay, so this is what is a normed vector space on which a real vector space on which a norm can be defined. Okay, or a definition for a norm exists. Next is the idea of something known as a Cauchy sequence. Okay, so let's say that this is a sequence. This represents a sequence, which essentially means that you have a1, a2, a3, a4, and so on, and this sequence is generated because of some operations involved. So a4 would be generated because of some operation depending on how depending that uses a1, a2, a3. Okay, similarly a5 would be generated for with the same operation. So basically this sequence is being generated with respect to some operation defined. Okay, something similar to what we had discussed in the previous lecture, where we are using the operation to generate a sequence which was essentially a better estimate of the actual solution trajectory. Okay. um, okay, so now a sequence an is called Cauchy if for every epsilon greater than 0, okay, there exists a index number given by n which is dependent on epsilon, such that norm of an minus am is going to be less than epsilon for all n and m greater than this index number capital N. Okay, so what this essentially means is, as you keep on generating sequences, suppose someone so what this essentially means that suppose someone tells me um, that I can you give me a part of the sequence so that the distance between or the norm taken as far as these sequence entries are concerned will always be less than, let's say, 0.1. If suppose someone gives this, I should be able to tell, okay, in this hypothetical example, n is equal to 100, so that if I take an entry from the sequence an minus am, the norm of this will always be less than this for nm greater than 100. Okay, so this means that after um, the 100th entry in the sequence, whatever entries you have in the sequence, the distance between any two entries that you pick up in the sequence after the 100th entry, there difference of the norm of the difference will always be less than the specified value epsilon. Now let's say that someone comes and tells me, no, I'm not satisfied with 0.1. I want to see if there are entries such that the distance between the entries in the sequence is going to be less than 0.001. I want them to be even closer. Let's say that I'm able to find out that n is nothing but equal to 1 lakh, okay, or 100,000. So in this case, what essentially it means that after the 100,000th entry in the sequence, I will be able to find. So basically, all the entries after the 100,000th entry in the sequence, if I take the norm of the difference between them, then it will be less than epsilon. And this norm of the difference is essentially the distance between any two entries after the 100,000th entry in the sequence, and this should hold true. Now, it doesn't, if you notice carefully the definition of Cauchy sequence, it doesn't say that for a given value of epsilon this should hold. No, it is saying that if someone gives you a value, you should be able to find a n, and this should be true for any value that is given to you. So no matter what value a challenger is giving you for epsilon, so I mean it's like you are being challenged in a way that this is the distance within which the entries of the sequence should always be. Then you should be able to tell, okay, if you look at the sequence after nth entry in the sequence, all the entries after nth entries of the sequence will be within the distance that you have specified, and you should be able to do this no matter what is the value of epsilon that is given to you. For any value of epsilon, you should be able to do this. Now if this is possible, then essentially the sequence is said to be a Cauchy sequence. So what this is essentially trying to tell you is, as you progress in the sequence, the entries in the sequence become closer and closer to each other. Okay, so n and m will be more closer to each other as this n increases. Okay, so as you move farther in the sequence, the entries in the sequence will be closer and closer to each other. So the distance between the entries keeps on reducing as you progress in the sequence. That is what is the property of a Cauchy sequence. Now note that if, as n approaches infinity, or as n approaches infinity, if an approaches to a value a, okay, then we say that the Cauchy sequence is convergent. Okay, so as you proceed in the sequence, you will see that as you go ahead and ahead, the infinite entry in the sequence will be a, and you would see that the entries in this uh, sequence, in this Cauchy sequence, are coming closer and closer, and they are actually becoming more closer, and they are becoming closer and closer to a, and a is the part of the sequence, and it is the infinite entry of the sequence. Okay, so this sequence will have a tendency to converge. So this is a convergent so Cauchy sequence in such case will be convergent. So um, please note that all convergent sequences are Cauchy sequences. But all Cauchy sequences are not convergent. Okay. For example, consider the set of rational numbers. Okay, we'll denote it with this Q. This is a set of rational numbers. Now, let us take a sequence of rational numbers, and the sequence is generated as this. The nth entry of the sequence is of this form: I equal to 0, n minus 1, alpha to the power I divided by I factorial. Okay, so the sequence that we have is A1, A2, and so on, AK. So we have an infinite sequence here. Now what you see is, as you progress in this sequence, you can verify that the distance between the entries in the sequence farther down the sequence keeps on reducing. As you move down the sequence, the distance between the entries in the sequence down the line keeps on reducing, so they come closer and closer to each other. Okay, now note that this is actually trying to converge towards what? This is trying to converge towards e power alpha, right? As you move farther down the sequence is trying to converge towards e power alpha. But e power alpha does not belong to a set of rational numbers. Okay, so in this set, limit n approaching infinity, a power n, this does not exist. So even though the distance between subsequent entries in the sequence as you move down the line of the sequence decreases, making this to be a Cauchy sequence, yet it is not a convergent sequence. Okay, another example that you can take is this: with a0 equal to 1 and an plus 1 to be equal to an plus 2 by an divided by 2. The sequence that you have is a0, a1, a2, and so on. This is again an infinite sequence. Okay, in the rational number set. Okay, so in this rational number set, this sequence that you see is actually a Cauchy sequence. It will satisfy the definition that you have for the Cauchy sequence. Okay, this is a Cauchy sequence. But As n increases, you are approaching um, is a value which is square root of 2. Okay, but square root of 2 again does not belong to the set of rational numbers. So limit n approaching infinity, a n, this does not exist. So there is no limit. The limit does not exist. Okay, which means that this Cauchy sequence in this set of rational numbers is not a convergent sequence. However, if this was a set of real numbers, then the first example that we have taken, e bar alpha, it would be a real number, and hence this Cauchy sequence will become convergent. Similarly, in the second example, root 2 being a real number, if the sequence is defined on a set of real numbers, then this Cauchy sequence also becomes convergent. Okay, so all Cauchy sequences need not be convergent, but all convergent sequences are essentially Cauchy sequences. Okay, now please note that we can define Cauchy sequences only over normed vector spaces, because if you see, the definition for a Cauchy sequence involves norms. Okay, so whatever we are seeing is on normed vector spaces. So Q is a normed vector space or set of rational numbers. This R is a non-vector space. This is a vector space we are considering with respect to real numbers. Now, a non-vector space V is called a complete vector space. Okay, if every Cauchy sequence that you can have on this vector space is convergent. Whatever Cauchy sequence that you can have on this non-vector space, if all of them are convergent, then the non-vector space is said to be a complete vector space. And a complete vector space is called a Banach space. So basically, a Banach space is a vector space where all Cauchy sequences are convergent. Okay, examples of Banach space here are R, Rn. Okay, these are all Banach space over any definition of norm. So the two norm that you know of is basically v1 squared plus v2 squared till vn squared square root, right? Where v is a vector with n tuples in Rn. Okay, so under this definition of norm, the vector space Rn is a Banach space. Okay, if a non-vector space is not complete, then we call it as a incomplete uh, vector space. Okay, so If not complete, then it means it's a incomplete vector space. Example, set of real numbers under the definition of 2 now. Okay, we, as a part of the proof for uniqueness in existence, we are interested in the set of continuous functions that map from 0 to delta to Rn. So another way of representing the same is essentially this. Okay, so this essentially, as we had defined, if C belongs to, if Y is a function that is in this set, then essentially Y maps the interval 0 to delta to Rn, and Y is continuous. Okay, so this set here, this vector space here, okay, or the set of reals with respect to the sup norm is a complete vector space. Okay, what is a sup norm? So Y being a function that belongs to this set, the sup norm of Y is essentially defined as the maximum value that mm, you have for over the entire interval 0 to delta. Maximum norm value that this Y will have over the interval 0 to delta. That is how the sup norm has been defined. So with this particular definition of sup norm, the set of continuous functions mapping 0 to delta to Rn is a complete vector space. Okay, so with this idea of on the preliminaries, we'll stop here, and in the next lecture we'll discuss the Banach fixed point theorem, which is also known as the contraction mapping theorem. We'll stop here. Thank you.